AM modes. AM and single sideband AM modes. All can be generated with the same basic transmitter structure. So CW transmitters are an oscillator, a crystal controlled VFO, and the VFO add a mixer for multi-band so that you can do more than one band. Otherwise, you're just like sticking a crystal in for 40 meters. You can do one. You don't need a VFO if you're doing that. It helps in order to go to a different frequency probably. A buffer, correct me if I'm wrong, Steve, a buffer is like I'm ahead of the speed I've told it to send it out. I've said to send it out at 20 words a minute, and I'm Superman on the Morse code, and I'm sending at 30 words a minute, and it will space it out to 30 by storing those extra characters until the buffer is full. Okay, and then spit it out at the speed you set it at. It reduces chirp as well. Power amplifier. Got to have something telling it, okay, so turn the power on. And it's nonlinear is okay on a CW transmitter. AM phone transmitters, a modulator between the oscillator and the mixer. AM, single sideband mixer, single balanced mixer, or an unbalanced or double balanced mixer. There's no yellow, don't stress out. Single sideband is double balanced mixer, and sideband filter. Okay, all amplifier stages following the modulator must be linear in AM phone transmitters. AM phone transmitters, signal should not occupy more bandwidth than that dictated by good amateur practice. We'll talk about what that is later. It's not defined.
So it's all about having an intelligible signal. Having a strong signal that's unintelligible doesn't help.
Yeah, the whole point is communicate. That's what the radios are for, is to communicate. You have to send an intelligible signal, and you don't need any more power, drive, or anything than what it requires to do that. Okay, on 60 meters, the limit is 2.8 kilohertz by regulation. You see 2.8 kilohertz on 60 meters?
And this is the only place in the spectrum where it is mandated rather than be good amateur practice.
A lot of people just avoid it. It's got its own special rules, power limits, all kinds of things.
And it's 5 dedicated channels.
Okay, FM transmitter structure. There's all kinds of parts there. Don't get scared by that. We're going to talk about it.
I want you to pay special attention to one thing here, okay? This is a 146 megahertz transmitter. With the crystal. It's 18 meg. What we're doing here is we were running it through a doubler here, and we're coming up with 36 meg here. This is a doubler, this is a doubler, and it gets out to here, and it's all of a sudden up at the 2 meter frequency. Doubling takes place here. What you're doing is you're tuning for the second harmonic. Tuning for the second harmonic. Tuning for the second harmonic. And that happens in nearly all modern radios. Because this crystal isn't going to oscillate at 144 meg. It's not going to do it. So we're going to use a lower frequency crystal, and then we're going to manipulate the daylights out of that thing.
I don't see how that works, but okay.
That's how it works.
Well, because I see 4 turns and I see 2 turns.
Well, and that's
That should be a half.
Well, and it's not. Yes, the turns ratio is going to be weird, but we're not talking about that. We're talking about the resonant frequency of the.
Oh, okay, okay. Of
this one is resonant at 36 meg.
Okay,
this one is resonant at 72.
Okay.
This one is resonant at 144.
Okay, and that's because we have a capacitor and an inductor, which makes a tank circuit.
Now you go ahead.
That makes more sense. I was like, wait a minute, it's having it.
No, it's not.
Yeah, okay. The resonant frequency of that tank. FM transmitter, not only is frequency multiplied, but deviation is too. So if you got some deviation in there, it's going to multiply it. Smaller deviation is easier to accomplish with low distortion. Amplifier stages do not have to be linear in an FM transmitter. Multiple stages, multiplier stages, by their very nature, are not linear.
What do we mean by linear amp? And why do we care?
Well, I know my answer is because the rules say we do.
Typically, the answer is cleanliness of your signal.
Okay, the bandwidth on FM transmitters, FCC limits your FM and PM transmissions to that dictated by, oh, there's that word again, and it's yellow. You need to know what good amateur practice is, but it's not defined.
There is no definition that is consistent one spot to the next to the next.
So it's kind of whatever the FCC says, or whatever the ARRL says, or whatever they think they don't like you doing. That's not good amateur practice. Okay, FM and PM have an infinite number of sidebands. Sidebands decrease in amplitude as difference from the carrier frequency increases. Bandwidth of FM and PM signals is BW equals 2 times FD plus FM in parentheses. So that is frequency deviation and the highest modulating frequency. But there's no yellow. That formula you don't need to worry about. Signal quality, testing your system. Ooh, there's a lot of that goes on out there.
Yes.
And there's a lot of people who don't know how to do a signal check or a signal report. First off, use a dummy load. We have an actual thing called a dummy load. Provides a load to your radio while testing. Its primary purpose is to bring transmitting signals over the air when making tests.
Yeah.
A basic dummy load consists of a non-inductive resistor. Now, a wire wound resistor is going to be inductive.
It's going to be frequency sensitive. It can't help it.
And a heat sink. So it's got to be non-inductive and a heat sink. So you could make your own out of a paint can and some mineral oil. A paint can full of mineral oil with a hole in the top, sealed, and all the resistors down inside. And the oil acts as the heat sink for the heat produced by the resistors that are absorbing all the power going out. They actually sell kits that you can buy that come with the mineral oil, or you can buy one where you go out to Walmart and buy your own mineral oil. Okay, transmitter signal quality. Overmodulation in AM modes distorts the audio, causes excessive bandwidth, and it's caused by talking too loudly, transmitter not adjusted properly, speak normally, adjust the microphone gain so that ALC peaks at but does not exceed 0. That's in yellow. Okay, transmitter structure, 100% modulation and overmodulation. So this is AM signal, and that's what it should supposedly look like. I don't know if that's really a good
That is a good representation.
It's a really good one?
Yeah.
Okay.
Now what you're seeing here is your audio waveform. Okay, so look what happens when you get into a normal system with sideband versus a distorted system. You see that clipping up there? You are losing part of your audio, and that comes out. This looks an awful lot like a CW waveform to me.
So when you talk about clipping, you see the nice triangle there, and then this one's got a flat top. Well, that's because this triangle was way up there, and now it's been just chopped off.
And what you have done here is you have caused your transmitter tubes or transistors to stop doing gain. You're topping out that transmitter. Same thing is happening here. See the nice clean valley there versus that spot right there where it's flat.
And the reason why these pictures are important is because some radios will actually show you that on your display. Okay, overmodulation AM modes, there's a two-tone test. It's in yellow. Two tones must not be harmonically related. Now, thankfully, you do not have to remember what the two tones are. You just need to know that the two-tone test, the tones must not be harmonically related. ARL lab uses that. Who cares? It's black. Analyzes the transmitter linearity performance. That's how an engineer would make sure that your radio is working properly. Observe the transmitter output on an oscilloscope or use a spectrum analyzer to observe spurious signals. Signal quality. Over deviation, FM and PM modes, excessive bandwidth, because you're over deviating. Audio distortion. Sounds familiar, right? If you're over deviating, you got all kinds of problems. Chopping of received signals, that's that flat top cutoff piece there on that oscilloscope picture that we had. Most transmitters have circuits to limit deviation. Key clips. CW is actually an AM signal 100% modulated with a square wave. I think we got a picture coming up shortly. Square wave consists of a fundamental and an infinite number of odd harmonics.
Boy, does it.
Therefore, a CW signal with a square keying envelope is infinitely wide. Key clicks are at a gradual rise and fall to keying signal. 2 milliseconds is key clicks. 8 milliseconds is no key clicks. So instead of just slamming the power on and off, it gives it a little bit of a little tiny bit of a ramp up. And there's the difference. So that's going to give you key clicks, and that tiny little bit is your millisecond. Now that's 2 milliseconds, and that's 8. So 8 thousandths of a second on the right-hand side there. And that will eliminate key clicks. Now, I've heard CW, I've never been able to figure out whether it had key clicks or not. Digital mode concerns. Adjust the signal so ALC never reaches 0 on digital modes. Overmodulation of a digital mode results in distortion, excessive bandwidth, splatter, and the inability of the receiving station to decode the signal.
And if you think we're making a big deal out of distortion, yes, we are.
Yeah. You want a nice clear signal, best you can get. Amplifiers. An RF power amplifier increases the transmitted output power from a transceiver. The single sideband / CW/FM switch on a VHF power amplifier sets the amplifier for proper operation in the selected modes. Linear and nonlinear amps. Linear amplifiers preserve the input waveform.
And that's the key phrase.
Yes, linear
The output
amplifiers.
waveform is identical to the input waveform.
They have low distortion, and they're suitable for AM and single sideband. Non-linear amplifiers do not preserve the shape of the input waveform. So just remember the linear ones do. That they have high distortion, and they're suitable for CW and FM. Because CW is just on or off, right? And amplifier classes A, AB, B, and C. Class A is on for 360 degrees or 100%. The entire cycle it's on. That is a question. The best linearity and the lowest distortion. They are the least efficient, so you're going to have to put more power into them. Class AB is on for greater than 180, so there's 180, but less than 360. That's a Class AB. It's a compromise between classes A and B. Class B is on for 180. It can be linear and it's more efficient. And Class C is the most efficient. And it's on for less than 180 degrees and is the most efficient.
But the only part of that signal that is being amplified is right here. That's it. The rest of it is being recovered with a tank circuit.
Say that again.
The rest of that signal, all of this portion right here,
The blue.
is being recovered in a tank circuit through a resonant tank. It's using this pulse right there to generate all the rest of this. Unfortunately, you get a fair amount of distortion this way.
But it works.
It works, does a hell of a job.
And it's the most efficient.
Yeah.
So, Class A, on for 360 degrees, 100%, and Class C is the most efficient. The question is going to ask you, what's the most efficient, I believe? And that would be a Class C. Through all that circuitry to amplify, it just goes straight to your radio. But when you transmit, it turns it over and stuffs it out through the amplification stages. Keying delay is added to the transmitter circuit, and it delays the RF output after activating the transmitter's keying line to allow time for the amplifier to switch the antenna between the transceiver and the amplifier output. Okay, so that is keying delay. It's clear as mud.
But that's the way the question's written.
Yeah. So it switches it between transceiver and, gives time and amplifier to switch the antenna between the transceiver and the amplifier output. So you don't want them instantaneously trying to go both ways, because one's coming in and stuffing one back out the other. And I give it, and it's not a lot of time. It's not like, oh, let me give it a second and a half here. No, it's
We're
just
talking milliseconds.
yeah, it's really quick. So the keying delay delays RF output after activating transmitter's keying line, blah, 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 amplifier output. It prevents what's called hot switching. Hot switching, opening or closing a relay while RF power is applied. Hot switching causes erosion of electrical contacts, excess heat, and reduces the life of the relay. The keying delay prevents hot switching. So that's why it's there. It makes your stuff last longer. Neutralization of amplifiers. Triode tubes and semiconductors are susceptible to self-oscillation due to stray internal capacitances. External components are added to cancel the effect of the stray capacitances. Tuning and driving. So look at what we got. What is that? What's that symbol? What kind of capacitor? Variable capacitor. And that is a inductor and variable inductor. Okay. Tuning and driving a linear amplifier. Three main controls: the band, the tune or plate, and the load or coupling. So I've got, let's see, you saw the little capacitor that you turn and the plates mash together. Okay. Larger ones of those in a box, and you got two capacitors and an inductor. And you dial those two in until you get the most noise you can hear. And you dial in the inductor until you get the most noise you can hear. And then you do a low power tune and see how your SWR is and adjust.
Now here's where the part that they're not telling. There's actually 4 components here, not just 3. The one you are not seeing is this guy.
Sure, it's right there. It says it.
Yes, that is a fixed radiator. What you are doing is you are tuning these 3 components to allow this fixed radiator to do its job. You're making a 4-component resonant circuit, not a 3-component.
But look at that. There's nothing yellow up there either.
What Dave's talking about is whether that's a tuning circuit in your amp or a outboard tuner. It's all part of the antenna system.
Right.
Okay, tuning and driving a vacuum tube linear amplifier. A lot of amplifiers are vacuum tube powered, even in the 21st century, but you can buy a solid state one. They say they're pretty slick. Set the amplifier meter to monitor the plate current. Set the amplifier to the desired band. Apply a small amount of drive power that's going to be from your radio. Adjust or tune for a pronounced dip minimum in the plate current. Be careful never to exceed the maximum grid current. Now, it's the grid of the tube.
And so what that is based on right there, that statement is the idea that grid is a very fine piece of wire inside the tube. What happens when you make a really tiny piece of wire and you add current to it?
Well, it depends. If it's properly designed, you have a light bulb.
Well, it's true, but what they're talking about here is the fact that wire is current limited. And you'll turn it into a fuse if you overcurrent it.
Okay, adjust the load or coupling control for desired output power without exceeding the maximum allowable plate current. So those 2 are yellow. They are on the test, and I think there's one more. Yes, repeat steps 4 and 5 until maximum power output is achieved.
Without exceeding.
Without exceeding the maximums for the plate or grid. So the key word there is on the first one is pronounced dip. I believe that's the only answer that has that is the correct answer.